Today I'm going to be talking about how we are securing Meta's production PKI credentials. So as you can imagine, Meta safeguards sensitive data across millions of hosts within our production fleet. And that data is protected and accessed by billions of credentials that we're using at any given moment. The confidentiality of that credential material is critical. Anyone with root access to these production hosts has the potential to maliciously attempt and maybe successfully access our credential management, compromise one or more of those credentials on those hosts, exfiltrate those credentials, and then use them from a less secure, less monitored environment to perform a prolonged attack to access the sensitive data. And that sensitive data is your data if you use any of our technologies. So think about how you would protect against this type of attack vector. Now, in terms of our background, as you can kind of imagine from the title of the slide, public key infrastructure is used heavily within Meta. Regardless of what is authenticating within our production environment, whether it be a user, a device, a client, a host, a laptop, a service, everything has a PKI credential. Now, if you're less familiar with PKI, a PKI credential is nothing more than an asymmetric cryptographic key pair with a private key that you want to protect at all costs and a public key that you freely share to perform authentication purposes. That public key is embedded within a certificate, and that certificate is signed by a trusted certificate authority. And we use these PKI credentials to securely connect and manage, transmit any data within our production fleet. So the end result is the security of our data in transit is tied directly to our PKI credential infrastructure. So if we have a scenario where we have the potential for someone with root access to compromise our credential management solution and be able to harvest those credentials and exfiltrate it, how can we protect against that? Well, the approach we ended up taking involved 4 key components: revocation, limiting mobility, hardening credentials, and then finally focusing on how we can prevent store now and decrypt later style harvesting attacks through post-quantum cryptography. Now, post-quantum cryptography we could probably cover that over an hour or 2 in the session, so we're not going to cover that today. But I'll point you to an engineering blog that we have on our public site that you can read about all of our efforts around post-quantum cryptography. But together, we believe that these efforts will improve the security posture for our data in transit within our production fleet. Now, every certificate that is minted has a validity period associated with it. As discussed in the Netflix talk, we were talking about short-lived certificates. Short-lived certificates can be have a validity period anywhere from seconds to minutes to hours to days, versus long-lived type of credentials that could be from days, months to years. A certificate is valid throughout that entire validity period. The only way to invalidate that certificate is to revoke it before its scheduled expiration. Revocation in of itself requires 3 main components. You have to have a detection mechanism that can determine if the credential has been compromised or potentially compromised. The certificate authority has to be able to consume that data from the detection system and build a revocation list. And then finally, you have the client. And the client is one of the largest drawbacks we have within the PKI infrastructure, because the client not only has to consume that revocation data from the certificate authority, but it also has to act on it. And anyone who's been involved in PKI knows that the client is the problem area, because they don't always do what they should do in those regards. So we can relatively consider revocation to be a reactive mechanism. And we wanted to shift our approach to being more forward-thinking around proactive solutions. And this is how we arrived at focusing on limiting mobility and hardening the credentials. So, With regards to authentication systems, we recognize that regardless of the safeguards that we put in place, we can't entirely eradicate exfiltration style type of attacks. So we look at ways to mitigate the usage of that credential in the event that it has been compromised. If you think about web-based authentication systems, like accessing your financial data, it's usually a mode where it has a username and password. And one way to protect that sort of credential system from being abused is by introducing multi-factor authentication. Multi-factor authentication takes something like the username and password, and ties it with something that you possess, like a phone or an authenticator app. You then, in order to complete that authentication, you must have both in order to access the data. Within our production fleet, we can actually leverage something very similar using an ambient two-factor authentication model with context-based awareness. We can take something that we have, like our credentials, and tie them with something that we possess, say an IP address. And that's essentially what we have done in our environment. When any entity in our environment is provisioned, there is a provisioning process that happens. A unique IP address is assigned to that particular entity and stored in a source of truth that is highly protected. We can take that information from that source of truth and embed it within the certificate process when we mint a new certificate. And then we can then leverage that information during a connection. We can compare the IP address that's defined in that certificate with the entity that's attempting to establish that connection. If they match, we allow the connection. If they don't match, we can block the connection. Now, there are multiple ways we could go about introducing this into the environment. We could do it during the TLS handshake, or we could do it downstream. We ended up choosing to do it downstream so that we didn't have to make adjustments to the way the TLS transport stack operated. Every time we establish a TLS connection, in order to access any of the data within the production fleet, we have to establish an RPC setup to perform any of those data transfers or data manipulation. So we actually invoke this during our RPC setup frame after the TLS connection is established, and we make that comparison then. And this solution isn't relatively novel. We have used types like this in the past. You can think of session binding. That's a process where, like a web app, will evaluate certain properties of a session and make a decision during that session's connection as to whether it should allow that session to continue or to terminate it. So session binding typically uses IP addresses as one of those mechanisms. So in terms of our deployment, how did we go about this? Because obviously introducing a solution like terminating connections could have significant ramifications in terms of usability of our services. So the first thing that we did before we began deployment is we introduced the IP binding extension within our certificate authority, and we started having that propagated within certificates as they were generated and or renewed. We then started observing what the behavior would be in the environment without any enforcement in play. And what we found was actually good in that the vast majority of systems connecting within our production fleet actually were using the IP address assigned to them. There was a small percentage, about less than 5%, that were not using the correct IP address. We were then able to catalog those systems. We identified what needed to be fixed in order to ensure that they were using the correct IP addresses. If it was a long-term fix, we added them to a temporary allow list to allow us to begin actual enforcement. And then we targeted certain certificate types within the environment, like a host certificate or a service certificate. And we began rolling this out, following a typical rollout strategy, targeting a specific service or entity, followed by a regional slow roll deployment, and then finally a global slow roll deployment. As it turned out, we didn't experience very many issues in that rollout because of the allow list that we defined. And as of today, considering that there are some other changes going into place, we can happily say we have about 94% of connections being enforced through this IP binding check. So the end result here is that we can effectively say that, by enforcing this check, the exfiltration is now moot, because if somebody were to compromise that credential, they can't use it off system. And so now we can rely on our detection systems within our production network to evaluate and determine if a certificate has been compromised and act accordingly. We'll continue rolling this out to the remainder of our certificate types and addressing any known mismatches so that we can get as close to 100% as possible. One way we can harden a credential and prevent prolonged attacks is by reducing the certificate lifetime. If we make it short-lived, then we have less concern around a prolonged attack, because that attack moves to more of a temporary type of nature. Within Meta, the majority of our production fleet does use what we define as a long-lived credential. From our purposes, we define long-lived as anything that is 4 days or longer. About 97% of these billions of credentials that exist within our environment are long-lived, with a good percentage of them roughly being around 3 months. So, the problem there is, by moving those to short-lived, we could have some downstream reliability issues, or downstream effects like service reliability that could impact us. So we looked at alternative ways that we could improve our credential strategy by hardening them. And that's where we started investing in trusted platform modules, a secure enclave that exists in our server fleet. Now, there is a slight issue with the usage of TPMs. TPMs are slow. Now, how does this impact us? Well, when you think about a TLS connection, when you attempt to establish a TLS connection, a handshake is performed, parameters are negotiated, and because we are using certificates as our credentials in this mutual authentication, in order to prove that the public key that's possessed in that certificate, that we have the corresponding private key, we perform a signing operation to complete that authentication request. Because the TPM is slower than other solutions out there, we're introducing milliseconds of latency every time we have to perform that signing operation. And when you have millions of hosts, billions of credentials, and every host have hundreds of simultaneous connections being handled at any given time, that introduces significant latency across the broader ecosystem, decreasing throughput. So that's not a good solution overall. So we evaluated other options, and that's where a relatively unknown TLS feature came into awareness for us, and that is introduced in RFC 9345. It's known as delegated credentials. Delegated credentials allows us to use a delegated short-lived token for our authentication during the TLS handshake process. So it introduced, there are a few benefits here. First, the delegated credential is minted locally. So we're not introducing another certificate in our credential system. And so we don't have a scale issue in terms of our certificate authority. Second, the delegated credential is not stored in the TPM. So therefore, it will not have that TPM-related latency for a signing operation. And then third, the delegated credential is short-lived. The RFC stipulates that it can have no more than 7-day validity period, and we can define what the maximum validity period within that time that we want to use. So, in terms of its functionality, this is what the new design kind of looks like. We still have a certificate authority. That certificate authority is still generating a PKI credential. That PKI credential is now birthed and stored within the TPM. The delegated credential is a separate asymmetric cryptographic key pair. So it has a private key and a public key. Those are not stored in the TPM. The delegated credential token itself is comprised of the public key and its validity period. It's signed by the private key of the PKI credential stored within the TPM. Now, when a TLS connection is established during the handshake, the client and server negotiate that they support delegated credentials. They then share their respective delegated credential tokens, and then to prove possession, they actually do a signing operation with the delegated credential private key. So the X509 credential or PKI credential is never used in the TLS handshake at this point. So this is how we move away from any latency concerns in the environment. Now, one thing I didn't mention that was on that slide was this attestation service. Attestation is an often overloaded term. You can roughly think of attestation as the ability to verify the integrity and authenticity of an asset using cryptography. It's a way to provide trust or prove trust. So the attestation service in this case performs two main functions today. The first is it wants to verify that the PKI credential was in fact birthed within a TPM. And then second, it can tie that particular PKI credential to a TPM on a particular host. So you can think of this as another layer of defense from a hardening and exfiltration prevention mechanism. And then how this is used is the attestation service provides an attestation statement that says it's verified these aspects using cryptographic measures. That attestation statement is provided to the certificate authority and then is evaluated during the certificate minting and embedded within the certificate as an extension, so that downstream components can also verify that data. Now, longer term, we also want to extend the capabilities of this attestation service. There's a concept out in the industry known as secure boot or measure boot. Essentially what this does is you can use an attestation capability to measure other components within the service and like firmware or hardware or attestation to verify that those properties are good. And so we could actually effectively take a system out of service if we detect that it's been maliciously manipulated. Say somebody uploaded a compromised kernel driver version. Now, as you can imagine, in order to use the TPMs for storage within the credentials, we actually had to take ownership of them. And we then provisioned the TPMs across the fleet, as we had previously not been using TPMs in any form in our environment. So we provisioned them during the base OS imaging, as well as during reboots for existing servers in the fleet. We also needed to prove their reliability, that the TPMs could actually be used in any form. So we built a reliability service that performs on an hourly basis a periodic seal and unseal operation using a key that was generated during the provisioning process against arbitrary data. And then we measured this over time, specifically 90 days. As it turned out, without any remediations in place, we were about 84 or 85% reliable. But this reliability work uncovered two main issues that we saw in our fleet. The first one being TPMs would enter into a shutdown mode, meaning the TPM thought it was under attack and would shut itself down. A reboot fixed that problem for us. The other one was what we classified as a transient issue, and it comprised of either the TPM responding with errata or just responding with timeouts. Those were the largest problems we saw, so we focused on those, and we built fixes in our provisioning service to attempt retries as well as changes in the kernel driver. And since we're using a Linux kernel driver, all of those fixes we actually published upstream into the Linux community so that everyone else could take advantage of those improvements. Those changes improved our reliability from 84% to 93%. And so we also needed to begin rollout. So one of the things that we decided to do was decouple rollout of delegated credential usage from having the PKI credential stored in the TPM because of those reliability issues we needed to solve. So we targeted delegated credential rollout against a set of a single service in our environment, did the same type of rollout, slowly et cetera. We had to build, obviously, the infrastructure to support delegated credentials, generate the delegated credentials, et cetera. And then as we verified things, we began moving to increase usage across the remaining widely distributed binaries or services within our fleet. And today we're seeing about 51% of new TLS connections using delegated credentials. We also set the delegated credential lifetime to be 2 days for our initial start. Why 2 days? Well, we felt that was a good balance, knowing we need to build in reliability and disaster recovery improvements into the environment so that we can quickly respond if there's an issue with a delegated credential that is shorter lived. Our long-term goal is to get delegated credentials to at least a lifetime of 1 day. I'd like to see us drive it lower than that. We'll see if we get there depending on the work we're focused on this half around reliability improvements. Unfortunately, we did have an incident with our rollout that I thought I'd share. We started moving towards having TPM signed delegated credentials. And in this particular case, a delegated credential was generated. It was being used by a critical logging service. And then 2 days later, that critical logging service could no longer establish TLS connections. The team raised an incident because they didn't know why they couldn't establish TLS connections. We investigated, and it turned out that the TPM went from being healthy to unhealthy. Delegated credential could not be renewed, and things failed. So we immediately disabled delegated credentials within the fleet and started doing remediations. We identified a number of things. Our client error message wasn't helpful to that logging service. They didn't know why the TLS session failed. We obviously did not detect that the delegated credentials had expired or they were not able to be renewed, so we needed to build better monitoring in place, and we needed failback capabilities if the TPM became unhealthy. So we introduced a way to detect if a TPM flips to unhealthy and stop using that delegated credential. This remediation work took about 50 days, and then we resumed our delegated credential usage without having them being TPM signed. Things looked good. We were back to 51% of usage. Things were great. We had all these remediations in place, and we started to roll out TPM signed delegated credentials again in June. As it turned out, we experienced another issue. TPM shutdowns became more prevalent as we started increasing usage of TPM signed delegated credentials. So if you remember, as I mentioned, we were about 93% reliability. That was at the end of June. By mid-July, we were at 100% deployment, and our TPM reliability had decreased to about 88, 89%. And it was directly correlated to the increase in our rollout of TPM signed delegated credentials. The good news is our remediations we put in place in the previous incident worked. We didn't break any services this time around. They were able to fail back, continue to connect, and use their X509 PKI credentials. And the TPMs are recovering as they undergo their standard maintenance cycles and are rebooted. The bad news is we haven't specifically identified the root cause of what's triggering the shutdown events. We've introduced tracing, we've gotten better data. We know it might be related to the TPM create and sign commands, but we haven't been able to reproduce an actual TPM shutdown event. That work is still ongoing. We also identified other fixes we could deploy in the environment. We identified another timeout issue in the kernel driver. We fixed that. We'll be releasing that upstream and rolling that out into the fleet. We're going to institute changes around what happens if there's consecutive failures, and we're improving the way we do health verification when we generate delegated credentials. So I'll end with a call to action. For those that are working on or with PKI, consider concerns that become more salient in large-scale production environments, even if your environment is not at the scale of Meta, because what we've built here, we believe, makes sense for other environments. Focus on developing steps to identify and remediate insider threats, implement short-lived credentials to reduce prolonged attacks, consider introducing IP binding mechanisms to mitigate exfiltration. And then finally, use secure enclaves like TPMs or confidential computing capabilities to trust to secure sensitive key material and use attestation techniques to verify that the sensitive key material does in fact reside within those secure enclaves. And with that, I'll open the floor to questions.